In this tutorial, we're going to have a look at this transmission mount. So as you can see here, this transmission mount allows elimination or reduction of vibration and shocks to be transferred to the transmission. So this model is composed with 3 parts. One of these parts is rubber, so we're going to be focused on the rubber side, rubber part, which is this. I can look at the material, check the material. So as you can see here, this is like a structural steel, and this is the rubber, and this one is also structural steel. So this is our model. So we'll look at the connections here. Is just 2 bonded contacts, because in the manufacturing process, this is literally vulcanized to the steel. So when we assign like a bonded contact here, it is simulating realistically what happens. So when you look at the mesh, it's as you can see, it's not a very coarse, it's not a very fine. Wouldn't be a big difference in terms of element size between rubber and steel, to avoid any kind of artificial stresses to be created. And one named selection that has to be created in order to tell Endurica what elements we would like to analyze. So in order to tell Endurica what elements we're going to be analyzing, we need to create a named selection separately of every rubber part. So if all the rubber parts are made of the same material, same rubber, so what we do is we create one named selection, and we include all the rubber parts inside that named selection. But as in this case here, we have only just one rubber part, so we have one named selection. And the boundary conditions here, so we're fixing this model here from this holes here, and we apply kind of one scenario of one cycle of mechanical loading, which starts from 0 and goes down to -8 millimeters and goes up again in 1 second. And this scenario is going to be repeated until failure. It's important to remind that the properties, the hyperelastic model that we assign in Ansys has to be the same as the one that we assign for the input file, the Endurica input file. Let's have a look at what we need basically for an Endurica compiled with Ansys fatigue life analysis. Basically we need an input file, and we need our Ansys file. So the Endurica input file is something that in this template, so you have a header, you name your model whatever, mount analysis or something, it's not important. Of the output, so after we get the analysis done, what kind of outputs we're interested in post-processing. So in this case, for example, we have mentioned, we have like input, we included life and critical energy density and the life sphere. So we wanted to see the amount of energies over time that cause the crack propagation. We want to calculate simply the most critical element to conclude the rubber part life, and we want to calculate the life sphere so that we would be able to define what is the critical plane where the crack is going to be propagating. We have here material analysis where we have included a height diagram if we are interested in observing the effect of strain crystallization of strain crystallizing materials on enhancing rubber's components life. So material analysis, so under the material analysis we have included a height diagram which allows us to observe the effect of strain crystallization on life, and we can smooth the diagram using this n number here. So under materials you can find the precursor size, the initial precursor size, the final precursor size. We have also the crack growth rate, where we can input the crack growth model's properties. In this case it's a Thomas model, so we need to input the RC, the TC, the F0, and finally we have elasticity model, where we have to input the in this case it's an Ogden model, so we need to input all the hyperelastic properties, and there is a name for this material. There is a name. That's all we need for our input file. So model is ready to run. So first of all we need to run an FEA model and wait for the analysis to get finished, so that we start running the Endurica solution and observe the evolution of convergence here. It's a nonlinear material, so it's a nonlinear analysis, which may cause some convergence problems if the strains are very high, or if the time step is very large. So we need to reduce it. So once the analysis is finished, as you can see, a full convergence and no any convergence problems. Full time is 1 second. This scenario, we get some maximum strain results, as you can see here. Some critical regions around here where maximum strains are observed, and yeah, so I'm gonna do this. So kind of like low strains, you can see here. We're going to see. So based on these very low strains, we can already expect that life is going to be something infinite. But in order to check this, in order to do the exact calculations, we need to call Endurica. So in my case, Endurica is already called here, as you can see here. Endurica is called, it's compiled already with Ansys. So in the get compiled, you need to go extension and go to install extensions. So browse to the browse to Endurica file inside the the C driver here, and browse to the latest version folder. So you can see here this 2025, but this is kind of like December 5th, which is like a newer update that I do have in my system. And then we browse to FEM interfaces here. So if you're using in Ansys, then you're gonna choose this one, but if you use Abacus or Mark, which are the two other FEM softwares that are compilable with Endurica. So I go to pick up the latest one here, and choose this WBEX file. As if in my case the extension is already installed, so we don't need to reinstall it again. Sometimes, not sometimes, when you install it for the first time, it doesn't have to be already existing in the interface. It doesn't mean that it's going to show up in the interface automatically. You need to double check that it is ticked here in the manage extension section here. So if this one is ticked, then it's going to show in the interface, but if it's not the case, then you should tick it here. So as you can see that almost everything is set. I do have my input file, I do have my analysis results, my strain histories, and it's time to switch. It's time to do the fatigue calculations in Endurica. So I go to Endurica section in my interface, and I click on export. So here we have like created a named selection that is automatically detected here as rubber, and the number of elements inside this rubber part. So what we do basically is that we choose this part. It's the only part that exists. So if we have multiple different rubber materials, so the possibility, you know, to choose all of them if we want to analyze them. This model was solved in one step. If there is any if there is any other steps, sometimes we may solve a model in like 2 steps, or just the first step is just installation step, which is repeated just once. It's not the step that is going to cause the fatigue and crack. It's conditioning. It could be pre-stress or something. That's why we don't have to pick that first stress in the result set. We only pick up the results, the time increments within the step where the duty cycle is assigned. So for this case, there is just one step, and it is the duty cycle. So we pick up every time increment that we do have here. And so the other thing that I need to do in this stage is that I need to tell Endurica where do I want to export the strain histories. For this case, I'm going to find my input file, of course. So this is the file where I'm going to append my strain histories. So I have named it. So if this one doesn't exist, I could have like created a new input file to which I have only histories, and I have only where the section where I append the strain histories. So later on I need to open that input file and I have to add the headings, the outputs. I need to add the crack growth property model, the hyperelastic model properties, and so on. But for this case, we have chosen this, and it says that this one is already existing, because when you choose this, it is naming, it is giving this file this name, so it is saying that it is already existing. I say yes. In this stage, I've only told Endurica where to append the strain histories. I need to set some other options here at the history before I export my strain histories to the input file. So we have like three dimensional elements. That's why we pick up the bulk 3D model. If we have like a 2D model, so we have this three choices to axisymmetric plane, or plane strain, or plane stress. So it's important to include the hydrostatic pressure, otherwise we're going to have like errors. If we have like a time dependent model, so we have to input the time, but in this case the time is 1 second, so the default is 1 second. We don't set any time period. It is by default set as 1 second. So we're not interested in temperature conditioning, so we leave this to default. So the other here is like for the ozone condition, the stride. So we leave everything in the as by default here, including this one. So if we have different rubber types within the same model, if we have picked here different element set, so we need to tell Endurica to treat this model as rubber by rubber, and that's why in this case we need to take this choice here. But in the case where we have only one rubber type, so by default it is considered to be just one. That's why we're going to leave it at default. So that's everything for this export option. We click on export and we wait for a couple seconds until the full export is done. So when the export is completed, we're going to have something like this. So we click OK, we close this, and we result of the export. As we have already appended the strain histories to the input file, we're going to have something that is added to our input. This did not exist. So this is so this is LE, so strain and history stress, and here the path directory to our DB file where the strain histories are contained in something like a binary file that contains the strain histories. As you can see, it's like a little bit lengthy, and if time increments are like smaller, and we have like a lot of elements, and we may expect a bigger model, so we may expect that the length of the KI file, the DB file, sorry, would be even bigger than 68 megabyte. Anyways, so now that we have our input file, we have appended the strain histories to our input file, so we're all set to run our Endurica calculations. Check that has to be done is that the hyperelastic properties that are assigned in the Endurica file has to be exactly the same as the ones that are assigned in our Ansys, in our FEA model. So let's double check this. So we have 032 here for mu1. So yeah, alpha 1 is 3.5 minus 0.054 for mu2. So as you can see that all these values that we have assigned in Ansys are the same in the Endurica file. Yeah, after doing this check, we should be all set to run the Endurica file. So in order to run Endurica file, I will launch a command prompt here, and I should say here, say Endurica space. So the name of my model is the name of my input file. So I'm going to search for this one. So the name starts with M. So I search for every file that starts with M. It is suggesting the DB file. I'm not going to run the DB file. And now that it is suggesting the input file, I'm going to run the input file. And I just click enter. So while Endurica is doing the analysis, it gives us some information about how much time is left for the license to get expired. Some information about the number of materials, the number of histories. So history is basically is a number of elements. So one element is considered as a history. And the number of threads. So if you're using a multiple thread license, you have the possibility to use multiple threads instead of just using one thread to make your analysis time cheaper. So we already have this analysis finished calculations. So once the calculations are done, we have some already information here: history, about life, about the critical plane. So the critical element is 5029. Life of the most critical element is something like 1.9 billion cycles. And the critical plane is 4.4. And when the Endurica analysis is done running, we have two files that are generated. We have this KM file. It's like a KM like M like message. There's like a message here where I am informed about almost everything that we've seen before. Then for the other file that is generated is the KO file. So the output file, O as output. So my results are here in this file, and if I click on this file, I'm going to have some information about the planes. When I read the 4.4 planes, I can look for the 4.4 plane and find the ID here is 4.4, and these are the coordinates according to the global coordinates. Okay. Next step is to import the output file. So in order to do that, I go to this tab here, Import Live. I have something that appears here called Fatigue Live. So basically it's saying Endurica output file to be browsed from here. I click here and I find my KO file, click, and I open the KO file. So the output is basically live, and the frequency is basically every result set. So I evaluate this result. We need to reverse this rainbow counter to have a better visualization, so that the red would be would be showing the most critical regions. So as you can see here that we need to change the scale here. We need to change the scale here so that we would be able to see the differences in a much more logarithmic scale. Let's pick up the logarithmic scale. So minimum, I need to pick up the minimum, yeah. So minimum is around here. So there is a little bit of elements being not dispersed in a homogeneous way, but you got the point. It's seen that somehow in this region, and as the model is asymmetric, so the same happens here. There's something like a failure to happen in a certain plane. This is basically infinite life, so whatever the failure would happen here after like 2 billion cycles, it's like a lot of cycles until failure. So if we want to get this to show a little bit more critical failure, we may be interested in changing the critical tearing energy. So the tearing energy is very high here. So in order to propagate the crack, you need a very high energy. So if we reduce this to 2000 instead of 15,000, for example, what happens? We're gonna save this and delete these two files, and then do the calculations again. Let's do the calculations again. Endurica. So I don't need this because we need to import a new output file for this case. So I delete this and I wait for the Endurica to finish the calculations here. It's more critical comparing to the other one. It's still very high, but as you can see that when the critical tearing energy is decreased based on the tests that we do, so based on the type of rubber that we're using, the critical tearing energy plays a very crucial role in the rubber's life. And import our life results again this way, and the counter is expected to be probably the same, but the value of life is, as we have observed before, it's going to be something less than we've seen before. Let's change this, reverse, logarithmic scale. So yeah, here is the most critical region. Pick up the minimum. So if we want to observe the Endurica viewer, I believe. yeah, if we want to post-process our results in the Endurica viewer based on the information that we gave here at the output section. So we wanted to output live critical energy density, live sphere, and the height diagram. That's why this the only thing that we're going to be able to see is this information. So if I click at the critical energy density, I can see over time. So CED history basically shows me over time what are the most critical energy densities that happens. We look at the live sphere here. So when we look at this sphere here, it is pointing the most critical plane. So when I look at this, so my most critical plane is something that looks like, yeah, it's like somehow on the YZ. So when I go to my model and I look at this YZ, so basically it's something that somehow it happens this way. Sorry. Somehow it happens this way. This way. So the crack starts to cut the model in this plane to this direction. It's not exactly YZ, but it's somehow around YZ. Most critical element is 5029. We're going to copy this and paste it here. It is showing where it is post. So basically this is a histogram showing every element. So all the elements existing in my rubber part are lined up in this axis. For the strain life map, we much more for the strain crystallizing materials. We have this possibility to map the life in a sort in a way to see the effect of strain crystallization on life. Yeah, so this is not a very strain crystallizing, I'd say. So I'm wondering if it's an area. So natural rubber is, I'd expect that this blue side would be would dominate a bigger space here to show how the strain crystallization is enhancing life by reducing the critical area. But this is the case for this one. So in case you're interested in observing these differences, you can make a comparison between two different rubbers. So that's all for this tutorial. I tried to cover almost every aspect that need to be known for like a beginner level CL, like most basic module to calculate life without combining any different duty cycles where like the loadings are time dependent, without considering the cyclic softening or any sort of material property time dependency. This is only one scenario that is repeated over time, like repeated a certain number of cycles until failure. That's it.